Okay, welcome back to your module 3. We are now on your unit 3. This is now the torsion of a thin-walled tubes. Okay, so torsion of thin-walled tubes. So in this unit, we will define what is shear flow, relate shear flow with torque, okay, and then identify the formula, or actually not to identify but to familiarize ourselves with the formula of the average shearing stress for thin-walled tubes. So we are now going to focus our attention on the effect of torque or torsion on a thin-walled tubes. Okay, so if you say tubes, that is a hollow, and then the wall or the material, the wall thickness of the material is very, very thin. So we can classify that one as thin-walled tubes. Okay, so torsion of a thin-walled tubes. So simple approximate formulas are available for thin-walled tubes. So these formulas are approximate, not that exact. But this is up to the time the simplest. This is the simplest solution acceptable for the analysis of a thin-walled tubes. Okay. So such members are common in the construction where lightweight is the paramount importance. Okay. For in case you need the member to be that strong, but at the same time lightweight, then your choice is not a solid. If we are talking about there a shaft, that is not a solid shaft, rather it is a tube. Okay, a tube, there's a space inside. So isn't it, we have that one in your circular shaft, we had also solid, we have also a hollow, but the difference of this thin walled tube with that hollow tube is that the thickness of this thin wall compared to the area is very, very small. Okay, the ratio of the thickness compared to the dimension of whatever is that dimension is very, very small, so that you can classify that one as thin walled tubes. Okay, it is very, very thin. Okay, so therefore, if that is the case, then in case we want to maximize that the material's strength to carry this certain amount of load, and then at the same time we should use a lightweight material, then your option is a thin wall. Okay, why? Because if that is a solid, then a solid actually is a solid will be in terms of weight, that is a heavyweight, isn't it, compared to a hollow or a thin wall. But a hollow compared to a thin wall is that the hollow we have a bigger thickness. Okay, so it means that is heavier compared to this thin wall. So your choice for a lightweight material is the thin wall. Okay, and at the same time, the idea here, why is it that we will try to make use of thin wall? Why is it that we will not use a solid, which is a smaller size? Because again, as I've said, the farther the point from the point of rotation or center of the rotation, the bigger stress on that part. So for us to maximize that one, we will just focus on the most farthest possible. Okay, so we will just consider the outermost. In case we are considering a circular shape, so I will consider the circular outer of the solid. So for me to maximize that one, then I will only focus at one. Maybe I can neglect the hollow inside, so that will make it a thin walled tubes. Okay, so again, if your important parameter in a design is lightweight, then this is what you should consider a thin walled tubes. So at this time, it is convenient to introduce the concept of shear flow. Okay, if this is the type of your member handling torsion, then we cannot just design this one, or we cannot just analyze this one just like a hollow. No, this is different. Okay, this is different because we cannot say that this is just like a circular shaft and so on and so forth. Because especially if we are talking about thin wall, that is not just a circular shape. Okay, that is not the circular shape. It could be a square tube, okay, it could be a rectangular tube, and so on and so forth. It could be this shape here, okay, it could be this shape here, it could be any shape. Okay, it depends on what is needed on the design. So at this time, it is convenient to introduce the concept of shear flow. So again, as I've said, shear flow is that in this design, okay, we can now, in these thin wall tubes, we can now assume, that's why we call this one approximate, because we can now assume, since that is very, very thin enough, then we can now assume that all the stresses on this cross section, on this wall cross section, are uniform. Okay, since again that is very thin already, so the difference of the radial distance of the points in this very thin material is not that big. So we can say that the entire stress for the entire cross section is uniform. So that is why it is approximate. Okay, so that shear that is being experienced in that cross section, very thin cross section, that is what we call as the shear flow. Okay, defined as the shear force per unit edge length of the needle surface. Okay, so that is shear flow. So torsion of thin wall tubes, this is the shear flow. We denote that one as Q. So shear flow, it is just a shear, but per thickness, per unit thickness. Unit thickness. That's it. Per unit thickness. So that is T over 2A, wherein your T there is the torque, of course, torque handled. Your A is, okay, area of cross section enclosed by the center line of the tube. Okay, what does that mean? The A is actually the area enclosed. But since, okay, even if that is very thin, there is still this, since we are referring now to area, the area, if I will consider the outer dimension compared to the inner dimension, is different, since now we are referring to the to area, not just distance. Imagine an area is a distance squared. Okay, so if you have a small difference in distance, that will be magnified because it will be squared. So to take into consideration the effect of that difference of area, which is big already, since that is an area, then we will be getting the average. Instead of deciding if that is the outer or inner dimension, then I'd rather use the center line. So that is to get the average. Therefore, if we are referring to A as the cross section, okay, enclosed, then I will be using the center line as my reference, the center of the wall. So look at this, that is the broken line. That is whatever dimension of that broken line here will be the one to be used to determine the area enclosed. Okay, so that's it. That is for our formula. So all I need to do is substitute. Just imagine your torque is Newton meter, your area is meter squared. So meter cancels, you will end up there with Newton per meter. Okay, so it is a flow. Force handled per unit, that is the shear flow. Okay, unit edge or unit edge length, or that is unit thickness. Okay, so that is shear flow Q. So in order for us to relate Q, that is the shear flow, it means that is the distribution of shear within the thickness. Okay, then for us now to get the average shearing stress, it means that is the one being considered as uniform. Okay, so this is now the average shearing stress. Okay, this is now the average shearing stress. So that is the one being considered as uniform. Okay, this is the one being considered as uniform, the average shearing stress on the within the area. Okay, so that is equivalent to Q, that is the shear flow, divided by T. Okay, the thickness, because again the Q is per unit thickness. Therefore, all I need to do is introduce the T for us to get the average shearing stress. So same thing, the only additional in here is the wall thickness. So that you will have here T over 2A times T below. That is your average shearing stress, okay, of the thin wall. So, okay, let's have this example. A torque of 600 Newton meter is applied to a rectangular section shown here. Determine the wall thickness so as not to exceed a shear stress of 8 megapascal. So that is our shear strength allowable, or allowable shear strength, 80 megapascal, and the one being handled, the torque, is 600 Newton meter. So we are finding in this dimension. So look at the dimension. This is important. Okay, the dimensioning here is look at this by the center line. The center of that is where the dimension is derived, not on the outside, not in the inside. So same thing here with the 80. So you can say that these are the center line, or the middle, okay, middle of the, or the center of the wall dimensions. So we do not need to worry about that later on to solve for the area enclosed, since the area enclosed should be the one enclosed by the center line. So again, thickness of that is the unknown. Okay, for that to handle the 600 Newton meter. and not to exceed the 80 megapascal. So go to the formula. Okay, shearing stress is, or tau is T over 2A T. But what is unknown is your T, thickness of plate, cross multiply. This is your formula. So all I need to do is substitute your T, which is 600 times 10 raised to 3. By the way, I am using a megapascal. So megapascal is, I want to break this down into Newton millimeter squared. So I'd rather transfer the Newton meter into a Newton millimeter. So multiply your meter into 1000 or 10 raised to 3. We'll make it millimeter. So the entire I will be using millimeter. Okay. So 2 times the area. What is the area? That is a rectangle. So center line dimensions. 80 times 30. That is the area enclosed. And then your shearing strength. That is the maximum. So that we will not exceed that. 80 megapascal. So look at this. Millimeter squared cancels with this. Newton cancels. So your thickness will be left millimeter. So that will be 1.56 millimeter. So that should be the minimum thickness for that to be handled, 60 Newton meter. One more example. Okay, a torque of 450 pound-feet is applied to a square section shown. Okay, so this is the section. And again, look at this. The dimensioning is on the center line. So no worry about that. So applied to the, but in case your dimensioning is inside and outside, you need to take into consideration later on in calculating the area enclosed by not considering that dimension given, if that is the inside or outside, but rather solving first for the dimension of the center lines. Okay. So, okay, determine the smallest permissible dimension A. That is the dimension A of the square, since that is a square. If the shearing stress is limited to 6,000 psi, so that is our allowable. Okay, 6,000 psi. So your torque, this is pound per square inch, 6,000 psi, pounds per square inch. So maybe I need to transfer that, since this is already pound, no problem. I need to transfer that in inch. So multiply it to 12, your 450 will become 5,400. So what we are finding is the dimension of the wall, which is A. Okay, since that is square. Solution, we will go back there. Okay, so what is the unknown is the dimension, so we can find that in the area. So I will bring out your area, rearrange of the area, T over 2T tau. Your area will be changed by the dimension squared, since that is a square. Okay, so A squared. So getting the square root of both sides, and at the same time substitute, of course. Okay, substitute. Your thickness is 0.10. Your allowable is 6,000. This will be 5,400. And then get the square root of that to get your A, that is 2.12 inches. Okay, so simple as that. And then let's have one more. Okay, a tube 2 millimeter thick has the shape shown. Okay, so this is a little bit complicated to solve the area, but actually once you know the formulas of different figures, then you can solve for this. Okay, 2 millimeter thick has the shape shown. Find the shearing stress caused by a torque of 600 Newton meter. So the thickness we are given to be 2 millimeter. That is the thickness of this wall. And then the torque being handled is 600 Newton meter. And we are finding the shearing stress on this member. Okay, thin wall member, shearing stress. So that is your tau. And then again, this is your formula. No need to rearrange. But your problem here, okay, your torque is that already. Your thickness is that. All we need to know is the area. So the challenge in this problem is the area enclosed. Okay. So since these dimensions here, okay, it means that this is a radius going to that, since actually this is a circular. Actually, that is half a circle. And so it is half a circle. So if I will try to divide, cut it here and cut there. This is semicircle, which if I will join, two semicircles will be equal to a whole circle, isn't it? Since the semicircles are the same dimension, then that means if I will combine these two semicircles, then that will make it as a whole circle of radius 10. And at the same time, what will remain here in the middle is a rectangle. So if that is 10, then it means that distance up to that point is 10, and this to that point is 10. Center line, these are center line dimensions, so no worry about the center line. So therefore, I can create a rectangle with a dimension, and that point here to point is 800 millimeter. That is the length of the rectangle, and the Width of that is 10 plus 10 will give us 20. So your dimension for a rectangle is 80 by 20. So the area of that is to be solved by 80 times 20. And then the area of a semicircle, twice of that will be a circle. Okay. So pi over 4 times the diameter. Okay. Diameter is 10, radius is 10, so diameter is 20 millimeter squared. So that is your area. Maybe you can compute of this and then substitute as a value, or you can directly calculate it here. So our formula again is T, near T. Why is it that I will not convert? Look at this. If this is millimeter squared, your meter there will be cancelled by the thickness. So for me, I will input the thickness to be in meter. Okay. Thickness. Sorry. Just a correction. Let me just correct this one. This is a correction. That should be millimeter. Okay. So this is 2 millimeter. So if I want for me to cancel that meter here, I will put that in meter. So that will be 0.002 meter. So meter cancels. But what will remain is Newton, and then this will become millimeter squared. So Newton millimeter will give me megapascal. So calculating will give us 78.36. So that is the average stress on this thin walled material. Okay, so that's it for thin walled materials. As simple as this. Okay, shear flow, that is the shear flow as I've said, that is actually the distribution of shear. And then if you are considering it to be uniform, that is your average shearing stress. Okay, so this is used to derive your average shear stress. So that is for thin walled tubes. Okay, thin walled tubes. So let's review some concepts. The area enclosed in thin walled tubes is computed from the center line of the wall. That is important. Okay, center line of the wall. The shear stress all throughout the wall is assumed to be uniform since the thickness is very small. Okay, so that is what I've discussed. So if you have any question, discuss that one on the live meeting, or you can comment below. So thank you very much for watching.